going to be giving another talk on Tuesday afternoon, which is not yet in the schedule. The exact time, David is just about to tell me. I presume it'll be probably 5 minutes after Jared's talk ends at 4:20 or something. Something like that. Okay. 3:40. Okay. So, all right. So I'd like to start off today talking about Hecke operators. And I'd just like to remind you, so there's a bunch of ways of thinking about them. And one thing that makes things very convenient is that by the Q expansion principle, you can tell everything about a modular form from its Q expansion. So one way you could think about the Hecke operator is simply to define it in terms of its action on the Q expansion. And it has a familiar form, namely TP applied to a Q expansion is equal to the following sum. So ANP plus P to the K minus 1 AN on P times Q to the N. So here is if P does not divide the level. And of course the weight is equal to K. So let me also just define a related operator called UP, which in some sense is defined in a similar way, but it's defined in level dividing P, and this is given as follows, sum ANP Q to the N. So here, this is now, you can imagine taking place at modular forms of level gamma 0 P. There's these two operations that preserve the appropriate spaces of modular forms. So these definitions, as definitions, aren't necessarily particularly enlightening. There's a bunch of different ways that are more natural in terms of how to think about it. And just returning to the very beginning of thinking about modular forms as functions on lattices, we can also write the definition in that sense. So namely, if we have a function on a lattice, and then you apply TP to it, how do you compute it on a lattice? Well, what you can do is you can take the collection of all lattices, lambda prime, containing lambda of index P. So there will be P plus 1 of these lattices. And you simply take the sum of the function over these lattices. And then, for various normalization reasons, you divide by P. So that's the definition of TP, just in kind of classical modular forms on lattices. And you can also define the Hecke operator UP in the same form. So now let's consider TP, sorry. Now let's consider UP of F. So here we're at level gamma 0 P. So if you remember, at level gamma 0 P, we had, for example, a lattice and another lattice of index P containing it. So here we actually want to evaluate on some extra information, namely, say, a lattice included inside, say, another lattice with index P. So how do we define the function here? Well, what you do is you simply have exactly the same sum, but now you have a distinguished lattice which has index P, which contains lambda, and you simply take the sum over all the lattices which contain it of index P that are not equal to your particular lattice. So instead of having a sum over P plus 1 lattices, you simply have a sum of P lattices. So these are similar definitions. This is a little more natural. And you can also start to write these things, and since I have 2 slides, you can just describe these things also in terms of the picture in terms of elliptic curves as well. So for example, if I want to define TP, say on elliptic curve, TP of, TP of F of elliptic curve and some differential, again, we're going to have a sum 1 on P. And so now what's the analog of these lattices which contain it of index P? these correspond to isogenies of degree p from this elliptic curve. So we can consider all isogenies from E to some elliptic curve D, which has degree p. So given such an isogeny from E to D, there's also a dual isogeny in the other direction, such that the composite is multiplication by p, and you take the following sum. So f, so now if you think about it on the other hand side, we would just take f of d, but we also have to write down some differential on d. So the way we get the differential is you take the differential on E and you pull it back using the dual isogeny. So pull it back. So it's just the same definition. And if we write down UP as well, again, we'll have the same definition, except we'll omit the special P isogeny that we come with. And again, you can also write this in terms of thinking about things on gamma 0P as elliptic curves with subgroups of index P inside the P torsion. Then, for example, if you think about pairs, say E and P, where P is inside EP of order P, well then, of course, the corresponding D are just equal to the quotients E modulo P. So there are P plus 1 possible P's, and of course there are P plus 1 possible P's. So there are a bunch of different ways of writing it in the same way. Okay. So if you want to compare, say, these second definitions to the first definitions, we need to be able to see what does the Hecker operator do to a Q expansion. Well, what's the Q expansion? The Q expansion is what you get when you just evaluate the function on the take curve. So you have to say, well, what happens if I just plug in the take curve? So you need to understand, if you have the take curve, what are the isogenies of degree P that start out with the take curve? So I won't do this computation in full, but let's just think about the take curve. So if you take the take curve and you take its P torsion, well, remember, we're thinking about this as, say, GM modulo Q to the Z. So the P torsion will certainly Q to the 1 on P is something that has order P. And similarly, zeta P is something that has order P. So to understand these possible quotients, you can just take the P plus 1 subgroups of that and take the quotients. So what do they look like if I take TQ and I mod out, say, by Q to the 1 on P times zeta P to the I? Well, it's not so hard to see. That's just the take curve of Q to the 1 on P, zeta P to the I. Just because I'm taking GM modulo Q to the Z, modulo this, which is then Q GM modulo this to the Z. And similarly, if I take TQ and I mod out by zeta P, well, this is a little more tricky, but it's not so hard to see. This is T of Q to the P, because you just imagine you have GM modulo Q to the Z. You take the P power map. What's the kernel of that? Well, somehow Q is going to go to the Q to the P, and the kernel is going to have the P through to unity. Okay. So now you start to imagine you take a sum. You want to evaluate the Heck operator on the take curve. You end up with a sum of the function evaluated at take curves like this, but you'll just get the corresponding Q expansions with Q to the P or with Q to the P and zeta P to the I, and you get the calculation in a similar way. Let me also remark that one should be a little bit disturbed by the fact that there's a 1 on P in the denominator here. That's not so great if you want to think about these actions of these operators in characteristic P. But one can get around that. I mean, one sort of way to get around that is first you define it this way. Then you think about it in terms of the Q expansion. And then you see that the Q expansion, you don't have to divide by P anywhere, well, as long as the weight is at least 1. And then using the fact that you have the Q expansion principle, you can make some argument of that form. Okay. But at least you can see that all these Heck operators work perfectly well in this algebraic setting. Okay. Actually, I have no idea when I'm supposed to finish, so let me just tell me that now. Otherwise, I just won't finish. 11:15. All right, thank you. All right, so what's next? The Hasse invariant. This is a modular form Well, it's defined really over any ring in which P is equal to 0. So, but it comes essentially from a modular form that will have weight P minus 1, level 1, and defined over Fp. And then from this, you get it over all Fp algebras. So this is a modular form. So what is it? Well, let me say it instead of kind of really giving a definition. I want to say it's characterized, in fact, over-characterized by the following properties. So on the one hand, it's a section of a line bundle to be weight P minus 1. So you kind of evaluate sections, but you can at least say exactly where their zeros are. And in fact, A has a simple 0. Simple 0. And in fact, the only zeros are at the supersingular points. So we know in characteristic P, there are finitely many supersingular points, roughly P on 12, P on 20, yeah, roughly P on 12. And this will just be a section that vanishes at those points. In fact, that already essentially determines A up to a scalar. But here's another way of determining completely, is that the Q expansion of A is 1. So it's a little bit funny to think about A as 1. I mean, it's not literally 1. 1 does not have the property that it vanishes at the supersingular points, because it's 1. But of course, what is this 1? I mean, it's not a function 1. The Q expansion is just evaluating it at the Tate curve. And you think about the Tate curve is a long way away from the supersingular points. It's way out at the cusp. And anything near the Tate curve looks ordinary. In fact, if you think about elliptic curves with, say, multiplicative reduction, you exactly model them by what is happening at the Tate curve. So the fact that this is what it looks like at a Tate curve is not a contradiction. I should also say it's not a contradiction with the Q expansion principle. I said that these modular forms are determined by their Q expansion. Well, A has Q expansion 1, and 1 also has Q expansion 1. But the Q expansion principle only works in a fixed weight. And since 1 is not a prime, the weight of the Hasse invariant is not 0. So it can't be compared in that sense with the constant function. So some other consequences which follow from what we've said already. Well, if P is at least 5, then this actually lifts to a modular form over ZP, and really, in fact, over Z. So then A lifts to Z. And in fact, of course, there can be many lifts. You can just, if you add P to it, P times the modular form to it, you get a different lift. But there are some particular lift that's sometimes convenient. So example, if you take the modular form given by the Eisenstein series, EP minus 1, that is a lift of the Hasse invariant. So all that says is that there's a modular form that's congruent to 1 mod P. That just follows from the Clausen-Stout congruences. Well, if P is 2 or 3, of course, it doesn't lift to characteristic 0 because it would have to have weight 1 or weight 2. There aren't many modular forms of that weight. But you can at least lift. Well, if you think of A, it's defined in characteristic 2. So if you lift it to somehow, you can see just by a kind of computation that A to the power of 4 is actually something that could be well defined mod 8. So this lifts. So this is now a modular form of weight 4. This lifts to E4, and A cubed modulo 9 lifts to E6. So the fact that these lift the specific forms is not really so important or even necessary, but it's sometimes convenient. For example, if you want to do various computations with Hasse invariants, it's sometimes easier to compute with these Eisenstein series because they're quite explicit in terms of their Q expansions. Okay. So it's a very nice modular form. I'm not really going to define it. The definition would take a little bit too long in proving these facts, and it's not necessarily going to be super enlightening. But nevertheless, it's a useful thing to have for basically the following reason. And if you don't really want to think so much about this construction, you can at least replace it even by some of these objects, at least to some extent. So using this, we can start to talk about p-adic modular forms. All right. So what do we want to, what's the goal in p-adic modular forms? Well, first, we want to think about two modular forms, and we want to think about congruences. So loosely, we'll just say two modular forms are close if they are congruent modulo high power of p. So things are congruent modulo power of p, that certainly makes sense. So we want to imagine putting some topology on the set of all modular forms such that they're close if they're congruent modulo p. Okay. So what we want to do, and I won't write this down, but morally what we want the p-adic modular forms to be is just the topological completion of the set of modular forms under this obvious topology. So let's see what happens if we sort of think about things in that way. So by abusive notation, I'll say let A in, say, coefficients in ZP, double brackets Q, be a lift of the Hasse invariant. So I've abused things in two ways here. I mean, this doesn't really make sense if P is 2 or 3, and A is really not really the best symbol to use for A, but you'll forgive me this. And one can easily avoid this issue, of course, if P is 2 or 3. But let's just imagine you have a lift. So we have one of these forms. So you can just prove, so we certainly have A is congruent to 1, it means 1 plus something in P, ZP, double brackets Q. So you can prove that A P to the n is congruent to 1 modulo P to the n plus 1, just as Q expansions. That's just, you can prove it by induction using the binomial theorem. So if we're imagining this topology in which two things are close, then we want to imagine that this AP to the n is close to 1, or in particular, that the limit of n goes to infinity of AP to the n is equal to 1, and also limit of n goes to infinity of AP to the n minus 1 is equal to 1 on n. So if we're going to just take the topological closure of all modular forms and then just get what we get, we're going to have to allow ourselves modular forms that look like 1 divided by A. And here A, you can imagine is just being EP minus 1, but you can imagine it being any lift of the Hasse invariant. So we're really inverting a huge number of modular forms. We're inverting 1 on EP minus 1 plus P times anything of that way. So there's really quite a few things we're inverting. But on the other hand, that's really the only thing we're inverting. So here's a kind of another way of thinking about it. So let's suppose that, so let B be invertible in the topological closure of all modular forms. So let's take, we just have, say, even a classical modular form B. Let's just suppose that there are modular forms, modulo higher and higher powers of P, such that when you multiply them by B, they're converging to 1. So then you imagine you have the following, where you have B times C is certainly the submodular form C congruent to 1 mod P. But if you then reduce this mod P, reduce mod P, you'll get BC equals 1. And we know what 1 looks like as a modular form. 1, well, regardless of the weight, 1 is only, the modular form with Q expansion 1 only has zeros at supersingular points. So if there are kind of classical modular forms whose product is 1 mod p, they can only vanish at supersingular points. So the only possible things that are invertible are really those forms that have 0 at supersingular points. Okay. So that's what we want to do. We want to define p-adic modular forms in some sense as things that we get when we invert all supersingular points. Okay. So let me draw a picture. So this is x01 over fp. Well, all right. It's just p1, it's nice and smooth. I'll draw a few points we know. There's a point called infinity. And then there are a bunch of supersingular points. I'm drawing 3 of them because for me, p is always 37. That's because I'm 37. All right. So now let's try to think what happens when we lift this to characteristic 0. So what's the inverse image somehow of this special fiber? So let's just draw a picture now. Well, now I have x01. So it's a Riemann sphere. You're looking at it from the front. You can pull back infinity. Well, certainly there's a specific point infinity that reduces to infinity. But then for these supersingular points, well, when you pull them back, of course, there's more than one thing that reduces to a particular point mod p. You can imagine if you have a parameter, and you think about the parameter just here being the J invariant, you can imagine, for example, all the J invariants that are congruent to that mod p when you pull them back. So somehow, what that looks like is you have these disks that are reducing to that. So here, you can imagine this is going to here. I guess the particular ones that matter, you have something like this. So this is somehow the pre-image. And so what we're imagining, for example, we have modular forms here, and we want to invert anything that's allowed to have, if it has zeros within this disk, then we're allowed to invert it. So it's somehow, once you start doing that, you start to sort of, the functions that you're left with are well defined in this region away from these disks, but they suddenly sort of no longer extend to anything inside this disk. If you're allowed to start inverting anything inside there, already you can just imagine building things up with poles sort of all around the boundary of this disk, and then you can't somehow extend your section into this disk. So therefore, so we can think about this. So I'll call these supersingular disks. They reduce to singular disks. And this I'll call the ordinary limits. It's not a disk. They're the points that when you reduce to them, you get ordinary points. So I include the cusp as well. And so what this suggests is that p-adic modular forms are really now the global sections. Well, this would just be somehow the global sections. I'm going to cheat a little bit by writing x01 and some moduli issues, but just ignoring that. This would just be the usual modular forms of weight k. Here, we're just going to restrict to this ordinary locus. So in other words, we just want to have functions, and we don't, because we're sort of allowing things to blow up anywhere along these disks, these functions will only extend as far as this region. And of course, the problem is that this is a little bit of an issue to make sense of this. I mean, this is certainly no longer, whatever it is, it's certainly no longer algebraic. I mean, it's some kind of thing. It's like a piece of Swiss cheese, really. It's like something with a bunch of holes in it. All right. So, sort of two ways of fixing it, or turning this into maybe mathematics. And somehow what we want to do is we want to give a definition of p-adic modular forms in some rigorous sense. So definition of p-adic modular forms. All right, so one thing we should do, we're kind of imagining the p-adic modular forms to be a kind of completion of a space of modular forms. So it would be really inconvenient to try to work over a ring like Z that isn't even p-adically complete itself. So I want to insist that I'm working over a ring R, which is a complete, with respect to P. So it's equal to its inverse limit modulo powers of P. You can just imagine somehow that R is equal to ZP or other things of this kind. So again, so how is it going to differ from modular form? So it's going to be, so of weight K, so it will be defined on pairs, just like for modular forms, of E on R, omega R, so omega R, again, a nowhere vanishing element of the differentials. But instead of, I mean, if we're just going to evaluate on this set, it's starting to look like a modular form. But we're only going to evaluate on the elliptic curves that correspond to the Swiss cheese region. So we're only going to evaluate things on the ordinary locus. But in terms of a rule, it's easy to kind of specify what that ordinary locus is. So this is somehow still part of this paragraph, defined on pairs such that, well, when you reduce it mod P, so when you replace R by, say, R mod P, and take the corresponding differential, so that this is invertible. So, of course, we're just imagining, for example, this was ZP in a field, we'd just be like saying, we're only going to evaluate elliptic curves such that when you reduce them to FP, you get something non-zero. So we're restricting the range that's going to allow a greater number of functions. And then once we restrict to this range, the definition is essentially the same. Namely, of course, it only depends on this pair up to isomorphism. If we replace the differential by some scalar, where here this is now a unit, it pulls out in the usual way. When you evaluate it on the Tate object, and the canonical differential, you get an element that doesn't have any negative powers of Q. That's the kind of cuspidal condition. And also it's compatible in the natural, so compatible with maps from R to S. So you have a modular form of a ZP and you evaluate it, and then you reduce the modular form mod P, you evaluate it, you get the reduction of that thing mod P, etc. So here is now a kind of algebraic definition that's sort of exactly representing what we want in that description. So I want to give some examples now of modular forms, of p-adic modular forms. So first, let's think about p-adic modular forms mod P. So what are somehow p-adic modular forms of Fp? Well, again, it's just like modular forms, except we can only need to evaluate them on the ordinary locus, which means we're evaluating them once we've removed the supersingular points. So in fact, what we get is exactly just the global sections. So here, this is over Fp, so if we just had modular forms mod P, we wouldn't have the supersingular locus, but here we're just allowed to have poles over the supersingular locus. So this is what the p-adic modular forms mod P are. So there's something a little bit funny here, which is namely, if you multiply this by A, or you divide by A, that should be, I mean, A is invertible on this region, so multiplication by A and division by A will be an isomorphism. So in fact, there's actually an isomorphism between this and, if you look at X, say, over Fp minus the supersingular points, and you evaluate it now in weight K, well, so now I'm just multiplying by some power of the Hasse invariant. So this will be, say, K plus P minus 1 M. So p-adic modular forms mod P, they don't only depend on the weight in a fairly weak way. If you change the weight by something that's congruent modulo P minus 1, you get the same thing. You're just multiplying by the Hessian invariant. So, but here's something else that we know. And let me just, okay, so this is certainly included inside here are certainly the modular forms themselves. So I'm going to give this a name. We'll call it K prime. So certainly the modular forms of weight K prime, well, I mean, of course, not everything that, I mean, you can just restrict it. That's just a restriction map here. And so on the other hand, there's a map from here. I mean, what these are really just the classical modular, these are the classical modular forms. So there's a map from the classical modular forms of weight K prime, where K prime is congruent to K mod P, but it could be bigger and bigger and bigger, which is mapping to this. And this is an inclusion, and this is an isomorphism. So certainly, the space of p-adic modular forms mod P includes all the reductions of all classical forms mod P for bigger and bigger weight, as long as there's some congruence condition on the weight. On the other hand, that's exactly everything. If you have any algebraic section in here, well, it doesn't necessarily extend over the supersingular locus, but it extends to a rational section that has some poles of some order, and you can just multiply out by the Hessian invariant to get rid of the poles. So anything in here comes from here from some bigger and bigger K. So already that's something interesting. We look at the p-adic modular forms mod P. What we get is all the modular forms, higher and higher weight, reduced mod P. That's one example. Here's another example. And this is maybe even the most important example. So suppose that F is classical weight K level gamma 0 P. And we'll just say it's also defined, say, over ZP. So the lemma is that F is a p-adic modular form. So what type of statement is this? Fortunately, I still have the definition of p-adic modular form. So we kind of have to compare what kind of objects these functions are defined on. So this guy here, F, so this is defined on pairs given, say, by an elliptic curve and a subgroup of, say, EP. That's the kind of, or like on P isogenies from ED prime, but this is a particular way of thinking about the model of this. So this is what F is defined on. And on the other hand, p-adic modular forms are defined simply on elliptic curves, but that are ordinary. So in order to turn F into a p-adic modular form, we have to do the following. We have to say, given such a function and given a pair of elliptic curve that's ordinary, how do we evaluate it? Well, to evaluate it, we somehow have to come up with a P. If canonically we can come with elliptic curve and construct ourselves a subgroup, then we're in good shape because we just define it by canonically finding that P and just defining it in terms of the usual definition. So, of course, there's a good reason. I mean, x0p in general is different from x01. If you have a function of level gamma 0p, you can't turn it into a function of level 1. I mean, certainly locally at any point you can choose a subgroup, but there's no way to consistently do that for all elliptic curves at once, just because otherwise it would be a map from x1 to xp rather than the other way around. So somehow geometrically or algebraically you can't do this. But we're giving ourselves more. We're giving ourselves that we're restricting to ordinary modular forms. And that's the key point, is that ordinary modular forms are special. So what we have to do is for an ordinary modular form, we have to construct such a subgroup. So let's remind ourselves what it means to be ordinary. If you take an ordinary modular form and reduce it mod P, and then take its P torsion defined over Fp bar, that is isomorphic to Z mod Pz. Right? So one way of, as Jared mentioned yesterday, elliptic curve, an ordinary elliptic curve in characteristic P has P torsion over a big enough finite extension. So now if we imagine taking, say, E over QP bar and taking its P torsion points, well, this is certainly Z mod Pz squared. There's a reduction map. And what we get then is canonically the kernel K, which is the kernel of reduction. Well, maybe I should have called it P. So we've done exactly what we needed to do. If you have an ordinary modular form, you can canonically come up with a subgroup of order P, and that does the job. So I think I want to describe this in terms of a picture to sort of explain what's going on. So I'm going to go back to my Swiss cheese. So I want to have the following situation. Okay. So here again is x01, a picture of it. So now I want to draw x0P. So, it's not important. All right. So it's going to look something as follows, and there's going to be a map down from here. So what we're really doing is actually this is actually a geometric map where we're taking something in the ordinary locus and pulling it back to x0p because we're finding a subgroup of index p. So let's draw some points that we know on this. So infinity, well, you know that pulls back to a point infinity, but it also pulls back to another cusp, 0. So let's see what happens when we take infinity. That's a computation we can do. That's the take curve. The P torsion on the take curve is given by Q to the 1 on P and zeta to the 1 on P. So we can just compute what the kernel of reduction is in this case. The kernel of reduction is exactly, I hope it's zeta P. Right? If you reduce roots of unity mod P, they all come to the same thing. So that's the kernel. And so when you pull it, you can pull infinity back, well, depending on how you label the cusp, but this is the canonical way. This gives you a way of pulling back infinity to the cusp infinity. If you choose a different subgroup, of course, all the other subgroups are of the form Q to the 1 on P times the root of unity. They're all isomorphic as subgroups. They all correspond to here infinity. So here you can think of this point here as being TQ with Q to the 1 on P, and this point here as being TQ and Q to the 1 on, this was zeta, and this is T to the 1 on P times some root of unity. Okay, so what happens is in the ordinary locus, we can start pulling back around some neighborhood of infinity, and of course we know we can't do it forever, because at some point we're going to get to the super single locus, and there's going to be some issue. But we can kind of draw geometrically what's going on. If I just draw it like this, you'll see that you have, I was going to put it as a region, but that's, since I shaded that region, it's probably a bad idea. So there's no color choice. So this non-shaded region here gets pulled back to this region here. Now you see the way I've drawn it. This is, say, a disk with 3 disks missing, and that corresponds to here. This is also, if you look at it, it's a disk. I got it right around with 3 disks missing. Yeah, this has got the Riemann sphere with 3 disks missing. It's also the Riemann sphere with 3 disks missing. So that already somehow implies a geometric relationship that's not so hard to check. If you think about the genus of this, it's going to be related, in fact, to the number of supersingular points. And you can kind of see it explicitly here in this geometric picture. Okay. So this is geometrically what's going on. But somehow this region on x0p is isomorphic to this region on x01, and they somehow are not distinguished. They kind of they're the same thing, and they're coming exactly from this construction. So this, here I was doing p is equal to 37. One thing that's nice about p is equal to 37, so it has genus 3, but also when you pull back to x0, 37, the points I in row disappear. So this one still has like an I in a row, but when you pull back, they're nice and smoothed out. All right. But maybe I should do an even simpler example, namely to do the example of somehow, again, n equals 1, and p is equal to 2. So here, let's go back to x1 over fp. So there's a point, infinity. So that's just j is equal to infinity. And then there's a supersingular point. Well, you know, for example, that there's going to be one supersingular point, and the j invariant, well, it's not so hard to compute what it is. J equals 0 is the supersingular point in characteristic 2. So let's now draw the picture here. This is going back to x of 1. And then we've removed some region, which is the pullback of j is equal to 0. This is the part where j has valuation less than 1. That's exactly here as j is equal to infinity. J is less than 1. That's the preimage of the supersingular point. So then the ordinary locus is just the region where j inverse, well, j inverse, if I can invert this correctly, it should be less than or equal to 1. So let's, for example, compute what are the p-adic modular functions. So let's compute, well, p-adic was 2-adic. 2-adic modular functions. Right, so of course, if we thought about classical modular functions, there aren't any, rather they're all constants. But here we started allowing ourselves to have lots of poles at arbitrary things. So now there are lots of things. For example, certainly J inverse, J inverse, it's here J is equal to 0 here. J inverse is a function on this region. In fact, any power of J inverse is a function on this region. But if you think about this, here we're really going to be talking about rigid analytic geometry. And if you don't know what that is, you should just think in terms of complex analysis. So let's try and think, what are the functions? Say if I take a complex variable z, what are the functions, complex analytic functions on z less or equal to 1? They're just power series whose radius of convergence is 1. And that's essentially exactly what happens in this case here. Namely, if you take h0 of x ordinary, and now we're looking at functions, this will just be equal, well, to power series in J inverse. So, well, maybe we want to pretend we're doing complex analysis, so let's really work over the ring C2, which is you take Q2, you take its algebraic closure, you get Q2 bar, then you take its completion, and you get C2, and then you take its algebraic closure, and you get C2 again. So it's like C. So, well, power series in J inverse that have radius of convergence 1, that's even easier to write p-adically. It's just n equals 0 to infinity, an j to the minus n, such that the limit of n goes to infinity of an is equal to 0. All right, because we're in the p-adic world, convergence is really easy. It's just power series like that. Nothing is more easy than just writing down this very simple thing. They're just power series on a disk. So Ken threw out the challenge last time of writing down various things with complicated numbers. I felt I should try to do the same. So I want to do at least one example. And I want to do an example of something that's not a classical modular form. So in fact, we have the following. We have E2, which is 1 minus 24 sigma 1n q to the n. N equals 1 to infinity. So this is not a classical modular form. But it is, in fact, a p-adic modular form for all p of weight 2. So, well, here I'm talking about p-adic modular functions. So what would that mean if I want to kind of write this in terms of a function? Well, how do you usually write modular forms in terms of functions? You want to convert them to weight 0. So I could take, for example, it's 6 power and divide by delta. And now this should be a genuine p-adic modular form of weight 0, well, except for a single cusp, sorry, a single pole at j is equal to infinity. So this should really live inside this power series ring, except there's an extra pole, so that you can probably allow a j to the 1 term. So you can just compute what it is. I mean, the computation is easy because you can somehow just formally invert, this is a power series in Q, J inverse is a power series in Q, you just write Q as a power series in J, and you formally invert it. So, of course, just as Q expansions, you can always do this regardless of anything. So 8 minus 4 minus 1, 9, 1, 8, 0, 8, J inverse, minus 1, 6, 4, 2, 7, 0, 5, 9, 2, J minus 2, dot, dot, dot. So you can always, of course, just in terms of Q expansions, write that. But the fact that this is a two-adic modular form means that what you get here will be something that converges two-adically. So this should be divisible by a bunch of powers of 2. It's divisible by 2. It's divisible by 4. That's as far as I can check. Okay. All right. So this looks like a great world in which we can now start talking about these things. And in fact, next time we'll see we can start to see hints of this in terms of Hidde theory of constructing eigenforms. But there's going to be a problem, which is namely that there are still going to be too many p-adic modular forms. And to give you a hint of what's to come, over convergent modular forms, well, I mean, you can guess what they're going to be. Instead of just having things on the ordinary locus, they're going to extend slightly further into this disk. And that is going to somehow make the difference. But in terms of, I mean, in terms of sort of it sounds sort of fancy, but if you think about it in terms of this, it's just going to correspond to power series whose radius of convergence is strictly bigger than 1. That will literally be the p-adic modular forms when n is 1 and p is 2 and the weight is 0. Just the union of all power series in J inverse whose radius of convergence is strictly bigger than 1. So these things are quite explicit.